Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclaire.
Welcome to Teolumen Insights, everyone. I'm Nathan Sinclaire, and we're diving into some seriously mind-bending physics today.
That's right. I'm Emma Greenwood, and we're tackling tachyons, those hypothetical particles that always zoom around faster than light.
Okay, I'll admit, the idea of anything traveling faster than light, it kind of breaks my brain a little.
It definitely challenges, our everyday understanding of physics, but that's what makes it so fascinating, right? And to make sense of it all, we're exploring the work of physicist Krzysztof Jodłowski. He's been digging into whether a consistent quantum field theory of tachyons is even possible.
So he's trying to figure out if these super speedsters can actually exist, according to the laws of physics as we know them.
Exactly. And, there's been some recent buzz in the physics world suggesting a connection between these superluminal observers, those traveling faster than light, and the foundations of quantum mechanics. Some think this could be a revolutionary link between relativity and quantum mechanics.
Hold on. A link between relativity and quantum mechanics. Now, that's something I'd love to wrap my head around.
It's a pretty big deal. But Jodłowski isn't convinced by some of these recent attempts to formulate a consistent quantum field theory for tachyons. He's taking a very critical look at a recent paper that claims to have done just that.
So he's playing the role of the skeptical scientist, putting these claims to the test.
Precisely. And he's not just throwing out opinions, he's got the mathematical arguments to back it up.
Okay, let's unpack this. Where does he even begin to unravel this?
Well, he starts by dissecting this idea of a twin space used in the paper he's challenging. It's a mathematical construct, a way of representing the states of these hypothetical tachyons.
Twin space. I'm already feeling a little lost in the theoretical weeds here.
Don't worry, we'll navigate this together. Think of it like a mirror universe, specifically designed to describe these faster-than-light particles. Now, Jodłowski discovered something really strange about this twin space. He found that the tachyon field, the mathematical description of how these particles behave, commutes at all points.
Commuting. That sounds a little too mundane for something as mind-bending as tachyons.
Right. But in the world of quantum mechanics, commuting has a special meaning. Imagine you're baking a cake. The order in which you add the ingredients matters, right? Well, in quantum mechanics, the order of operations also matters. But if something commutes, it means you can swap the order and it doesn't change the outcome. It's like adding the flour before the eggs. Suddenly it doesn't matter.
So Jodłowski is basically saying that these tachyons, at least in this twin space formulation, are acting like they follow the predictable rules of our everyday world, not the weird fuzzy rules of quantum mechanics.
Exactly. And that's a huge problem because quantum uncertainty is kind of a big deal in the quantum world. If these tachyons don't follow those rules, it throws the whole idea of a consistent quantum field theory out the window.
It's like trying to fit a square peg into a round hole. They just don't belong together.
That's a great analogy. And Jodłowski doesn't stop there. He goes on to examine another crucial aspect of this proposed tachyon theory, the Feynman propagator. Now stay with me here. A propagator is like a map that tells you all the possible paths a particle can take through space-time.
So it's like a cosmic GPS for particles.
Exactly. It helps us predict how particles move and interact. The paper Jodłowski is challenging relies on a specific type of propagator called the Darcy-Darcy propagator. It's been around for a while, but Jodłowski throws a wrench in the works by showing that this propagator actually violates a crucial principle called unitarity.
Okay, unitarity. That sounds important. What does it actually mean in this context?
Think of it like this. Imagine you're flipping a coin. You have a 50% chance of getting heads and a 50% chance of getting tails. Right. Those probabilities add up to 100%. That's what unitarity ensures in the quantum world. All the probabilities of all possible outcomes, they always add up to a neat and tidy 100%.
So it's like the universe's way of keeping its books balanced.
You got it. But Jodłowski demonstrates that with the Darcy-Darcy propagator, things get out of whack. The probabilities don't add up properly, which means the theory isn't playing by the rules of quantum mechanics. It throws consistency right out the window.
So if this tachyon theory violates unitarity, it's basically saying that the universe's accounting system is all messed up.
That's one way to put it. And that's a big problem if you're trying to build a solid and reliable theory of these superluminal particles.
This Jodłowski guy, Really doesn't pull any punches, does
He
it?
definitely takes a rigorous approach, and his critique gets even deeper. He delves into the concept of negative mass squared, which is a key idea when talking about tachyons.
Okay, negative mass squared. That definitely sounds like we're venturing into uncharted territory. Break it down for me. What does that even mean?
Think back to Einstein's famous equation, E mc all rho. It tells us that energy and mass are fundamentally connected. For ordinary particles like electrons, their mass squared is always a positive number.
Makes sense. Mass is basically a measure of how much stuff a particle has, so it should always be positive.
Right. But tachyons are weird. Their mass squared is hypothetically negative. It's like they have some kind of anti-mass.
Anti-mass, that's just wild. What kind of implications does that have?
Well, one consequence is that as a tachyon gains energy, it actually slows down, getting closer and closer to the speed of light, but never quite reaching it. It's almost like the speed of light is a cosmic speed limit, a barrier they can approach but never cross from the other side.
So these tachyons are like speed demons, forever stuck in a cosmic traffic jam. Always pushing the limit, but never quite breaking free.
That's a great way to picture it. And this negative mass squared leads to all sorts of other bizarre consequences, which Jodłowski carefully examines in his analysis.
This is already a lot to process, but I feel like we've just scratched the surface. There's still so much more to explore in Jodłowski's work.
You're absolutely right. He also tackles some really intriguing concepts like micro-causality, the LSE formalism, and even virtual tachyons. Are you ready to dive even deeper into this rabbit hole of theoretical physics?
I'm definitely game. Let's see what other mind-bending insights Jodłowski has in store for us.
All right, let's talk about micro-causality. This is the fundamental principle that cause must always come before effect. It's kind of a big deal for how we understand the universe.
Yeah, I can't imagine a universe where things happen in reverse order. It'd be pure chaos.
Exactly. But tachyons, those pesky faster-than-light particles, they kind of throw a wrench into this whole idea. If something can travel faster than light, it could theoretically arrive at a destination before it even left its starting point. It'd be like watching a movie where the climax happens before the introduction.
Okay, that's giving me a serious headache just thinking about it. So is Jodłowski saying that tachyons could actually break the rules of cause and effect?
He's definitely concerned about it. He points out that the way tachyons are represented in some of these proposed theories, especially in the way they use the Feynman propagator, can lead to situations where effects seem to precede their causes.
Wait, remind me again, what's a Feynman propagator?
Right, we talked about it earlier. Think of it like a map that shows all the possible paths a particle can take through space-time. But Jodłowski argues that for tachyons, this map might be leading us astray, allowing for these bizarre causal paradoxes.
So it's like those tachyons are taking shortcuts through space-time, messing up the natural order of things.
That's a great way to put it. And this potential for causal chaos is one of the biggest challenges for building a consistent theory of tachyons.
It's like trying to solve a jigsaw puzzle where the pieces keep changing shape.
Exactly. But Jodłowski doesn't just point out the problems, he also explores some really intriguing possibilities, like the idea that maybe, just maybe, the order of events isn't as absolute as we think it is.
Wait, hold on. Are you saying that time might not always flow in a straight line?
Well, it's not quite that simple, but there are some hints from quantum mechanics that suggest time might be a little bit more flexible than we've traditionally thought. There's this concept called superposition, where a quantum system can exist in multiple states simultaneously until it's measured. Some physicists believe that this idea of superposition might apply to space-time itself, allowing for events to exist in a kind of causal blur, where the order of things isn't fully determined until an observation is made.
Whoa. That's seriously blowing my mind. So you're saying that the act of observing something might actually determine the order of events?
It's a wild idea, but it's one that some physicists are taking very seriously. And it might be a way to reconcile the mind-bending world of tachyons with our intuitive understanding of cause and effect.
This is why I love these deep dives. We're venturing into the territory where physics starts to sound like philosophy, where the very nature of reality is up for debate.
I know, right? And Jodłowski isn't afraid to grapple with these profound questions. He also takes a deep dive into the Quantum Principle of Relativity, or QPR for short. It's a framework proposed by physicist Andrzej Dragan that tries to bring superluminal observers into the fold of quantum mechanics.
Okay, Quantum Principle of Relativity. Anything with quantum in the name is usually a wild ride.
You can say that again. QPR is all about reframing how we think about space and time. It suggests that what we perceive as a universe with 3 dimensions of space and a 1 dimension of time, it might actually look completely different to a superluminal observer. They might see it as a universe with 1 dimension of space and 3 dimensions of time. It's like space and time are switching places.
Whoa, that's a serious mind flip. So to a Tachyon zipping around faster than light, what we see as distance might look like time to them and vice versa.
Exactly. It's like trying to imagine seeing the world through the eyes of a being that experiences reality in a completely different way.
That's both fascinating and utterly confusing at the same time.
I know. And that's just scratching the surface of QPR. It also introduces this idea of a twin space, which we mentioned earlier. This twin space is a mathematical construct that supposedly allows for superluminal observers to exist within the framework of quantum mechanics.
But wasn't that twin space where Jodłowski found those issues with the Tachyon field commuting at all points?
That's right. So while Jodłowski acknowledges that QPR is an interesting attempt to reconcile superluminal motion with quantum mechanics, he ultimately raises some serious doubts about its validity.
It's like QPR is trying to build a bridge between two continents, but using materials that are fundamentally incompatible.
That's a great way to put it. Now, speaking of bridges, Jodłowski also examines another important framework in quantum field theory, the LSZ formalism.
Okay, the LSZ formalism. That sounds pretty technical. What's the gist of it?
Think of it like a set of rules for understanding how particles scatter, how they bounce off each other like tiny billiard balls in the quantum world.
It's like the rule book for those cosmic billiard games we were talking about earlier.
Exactly. But Jodłowski argues that the LSZ formalism, it runs into some serious trouble when you try to apply it to Tachyons.
What kind of trouble?
Well, the LSZ formalism relies on something called the asymptotic condition, which basically says that in the far past and far future, particles should act like free particles, uninfluenced by each other. It's like saying that before and after a billiard game, the balls should be moving in straight lines, undisturbed by each other's presence.
That makes sense. You need that initial and final state of free particles to have a clear picture of what happened during the scattering event itself.
Exactly. But for Tachyons, this asymptotic condition breaks down. Because Tachyons are always traveling faster than light, they're constantly interacting with each other, even at vast distances. It's like those billiard balls are constantly swerving and curving, never moving in straight lines.
So it's like trying to analyze a billiard game where the table is constantly tilting and warping, making it impossible to predict the trajectories of the balls.
Precisely. And that unpredictability, that lack of clear asymptotic behavior, it throws a wrench into the machinery of the LSZ formalism, making it very difficult to calculate scattering amplitudes for Tachyons in a consistent and reliable way.
Okay, I'm starting to see a pattern here. It seems like whenever physicists try to apply our current understanding of quantum field theory to Tachyons, things start to break down, rules get violated, and paradoxes pop up left and right.
You're absolutely right. And that's the heart of Jodłowski's critique. He's pointing out these fundamental challenges, these deep inconsistencies that arise when we try to force Tachyons into a theoretical framework that might not be equipped to handle them.
It's like trying to squeeze a giant squid into a goldfish bowl.
Exactly. Now, let's talk about another fascinating concept that Jodłowski explores, virtual tachyons.
Virtual Tachyons. Those sound even weirder than regular Tachyons.
They are pretty strange. Remember how we talked about virtual particles earlier, those fleeting phantoms that pop in and out of existence in the quantum vacuum? Well, virtual tachyons are like the super speedy cousins of those virtual particles. They're even more ephemeral, more ghostly.
So these virtual Tachyons are like those fleeting glimpses you catch out of the corner of your eye. Something you think you saw, but can't quite be sure.
That's a great analogy. And even though these virtual tachyons might be incredibly elusive, Jodłowski suggests that they could still have real, measurable effects on the behavior of other particles.
So even if we can't directly observe these virtual Tachyons, they might be subtly influencing the world around us.
Exactly. Think of it like this. Imagine you're watching a play. The actors on stage are the real particles, the ones we can directly observe. But behind the scenes, there's a whole crew of stagehands, lighting technicians, and sound engineers who are working hard to make the show happen. Those behind-the-scenes players are like the virtual particles, subtly influencing the performance without ever taking the spotlight themselves.
That's a great analogy. So these virtual tachyons could be like those hidden stagehands tweaking the laws of physics behind the scenes.
Precisely. And Jodłowski suggests that their contribution to particle interactions could lead to some very interesting and potentially observable effects.
Okay, so how do we go about detecting these phantom tachyons? Do we need some kind of superpowered ghost-busting equipment?
It's not quite that dramatic. Jodłowski points to some specific phenomena that might be influenced by the presence of virtual tachyons. For instance, he discusses how they could affect the scattering of other particles, those interactions where particles bounce off each other like tiny billiard balls. The presence of virtual tachyons could subtly alter the angles and energies of those scattered particles, leaving a telltale fingerprint that we could potentially detect in experiments.
So it's like those virtual tachyons are leaving behind subtle clues, hints of their existence hidden within the complex interactions of the quantum world.
Exactly. And those clues could potentially lead us to a deeper understanding of these elusive particles and their role in the universe.
This is what makes science so exciting. It's like we're detectives, piecing together evidence from the tiniest clues, trying to unravel the greatest mysteries of the cosmos.
Couldn't agree more. And in the case of tachyons, it seems like the mystery is only deepening as we explore their implications for our understanding of space, time, causality, and the very nature of reality itself.
This is definitely a deep dive that's left me with more questions than answers, but I'm definitely eager to keep exploring.
Me too. Now, are you ready to tackle a couple more mind-bending concepts that Jodłowski throws into the mix?
Bring it on. I'm starting to get used to this whole brain-stretching experience.
Okay, let's talk about Fock space. Now, this one's a bit abstract, but stick with me. Imagine you're trying to describe a system with, not just one or two particles, but a whole bunch of them. Like a beam of light with countless photons, or a metal with a sea of electrons.
Okay, so we're talking about systems that are way more complex than just a single particle bouncing around.
Exactly. And that's where Fock space comes in. It's a mathematical framework that allows us to describe the states of these complex, many-particle systems. Think of it like a giant chessboard, where each square represents a different configuration of particles.
So instead of tracking individual particles, we're looking at the overall state of the entire system.
You got it. And Jodłowski brings Fock space into the picture when he discusses the challenges of constructing a consistent quantum field theory for tachyons, especially when you start considering interactions between multiple tachyons.
So it's not just about figuring out how one tachyon behaves, but how a whole swarm of them might interact and wreak havoc on the laws of physics.
Pretty much. And the way tachyons are represented in Fock space, particularly in this twin space formulation, leads to those pesky commutation relation problems we keep bumping into.
Right, those rules about the order of operations in quantum mechanics. It seems like those commutation relations are the bane of these tachyon theories.
They really are. And Jodłowski uses Fock space to show how these inconsistencies pop up, highlighting the deep mathematical challenges of incorporating tachyons into our current understanding of quantum field theory.
So it's another piece of evidence suggesting that our current theoretical tools might not be up to the task of taming these superluminal speedsters.
Exactly. Now, one final mathematical tool that Jodłowski uses to scrutinize these tachyon theories is the Lorentz transformation.
Okay, the Lorentz transformation, that rings a bell. It's something to do with Einstein's theory of relativity, right?
You got it. The Lorentz transformation is all about how measurements of space and time change, when you look at them from different reference frames, especially frames that are moving relative to each other. It's a cornerstone of special relativity, ensuring that the laws of physics are consistent no matter how fast you're moving.
So it's like a mathematical lens that lets us see the universe from different perspectives.
That's a great way to think about it. And Jodłowski uses the Lorentz transformation to examine the covariance of these proposed tachyon theories.
Covariance. That sounds important. What does it mean in this context?
In essence, it means that a theory should hold up. Its prediction should remain consistent, even when you view it through the lens of the Lorentz transformation. It's like saying that the rules of physics shouldn't change just because you're looking at them from a moving train or a speeding spaceship.
Makes sense. The laws of the universe should be universal, right?
Exactly. But Jodłowski finds that these tachyon theories, they actually struggle to maintain covariance under certain Lorentz transformations, particularly those involving boosts that change the sign of energy. It's like the theory starts to crack and crumble when you push it too far outside its comfort zone.
So it's another sign that these theories might not be as robust as we'd hoped.
That's right. Jodłowski's analysis, using all these mathematical tools, Fock space, Lorentz transformations, canonical commutation relations, It really highlights the immense challenge of building a consistent theory of tachyons. It seems like they just don't fit neatly into our current understanding of quantum field theory.
So where does that leave us? Are tachyons destined to remain forever in the realm of science fiction?
Well, not necessarily. Jodłowski's critique isn't meant to shut down the conversation about tachyons. It's more like a call for deeper exploration, for new and more creative approaches. Maybe there's a completely different framework out there, one that we haven't even thought of yet, that can accommodate these superluminal speedsters.
It's like we need a whole new set of tools, a new language even, to begin to describe these particles.
Exactly. And that's what makes this whole area of research so exciting. We're pushing the boundaries of what we know, challenging our assumptions, and expanding the horizons of human knowledge.
It's a reminder that the universe is full of mysteries, and we're only just beginning to scratch the surface of its deepest secrets.
And who knows, maybe one day those seemingly impossible tachyons, they'll lead us to a whole new understanding of physics, a new paradigm that revolutionizes our view of reality.
Well, that's a deep dive I'd definitely sign up for. To our listener who sent us down this fascinating rabbit hole of tachyons, thank you.
And to all our listeners, thanks for joining us on Teolumen Insights. Keep those minds curious, and we'll catch you next time.